Hi there, this is Dave Nguyen, CEO of Brain Technology and inventor of the LCPC transform. And in this talk, I'm going to talk about applying the LCPC transform to measuring spine curvature shapes in scoliosis. To begin, let's talk about how the LCPC transform works. So in step one, say this is the shape of a spine curvature. And once you've outlined it by hand or extracted this mask from an automated image processing pipeline, you can then define the baseline, right, as we did here in green in step two, at which point you can apply a grid system. In this case, I applied the parallel grid system onto the shape. And this allows you to calculate the distance of every intersection between a grid line and the blue line, right, relative to the baseline. This distance calculations, or these calculations, give you the data in step three, that is position and distance. Once you get data in this form, you can then, if you want, plot it to visualize it, which is not necessary, but we do it just for illustrative purposes. Of course, every intersection or every radial line that intersects more than one blue line, those two distances are summed together so that there's only one value for each position line. All right, the next step is to then do the fast Fourier transform on the data from step 3 or 4, which results in a frequency plot. And this frequency plot is a multi-dimensional representation of the shape that you began with in step 1. The versatility of the LCPC transform also allows you to create an index based on this frequency plot. That is, in step 6, you could simply sum all the bins, all the bars in the frequency plot to derive one number that represents the shape that you began with. Or you can find other ways of creating indices based on the values of these bins, which we will do so later on in this presentation. But in this way, the LCPC transform allows you to turn a two-dimensional shape into a simple scalar value that represents that shape, which is great for machine learning, but also intuitive to a physician. So here are the types of scoliosis. I will show examples of a few of them in this presentation. In particular, I create a phantom series representing the thoracolumbar category of scoliosis. So here, this is a line that represents the middle of the spine. As you can see from left to right, the patient begins to improve, right? And this is a phantom gradient starting with shape 1, in which I just shrunk, right, or I compressed horizontally to eventually reach the relatively straight line in sample 5. So when we applied the LCPC transform to this gradient, right, what we found that by simply summing all the bins, right, in each frequency plot, we were able to derive a nice linear trend representing the shape change as the patient improves from state 1, 2, 3, 4, 5, right, all the way to normal. Okay, and this is an example of how precisely the LCPC transform can measure shapes that are complex and that are open shapes, but in ways that the human eye has a hard time assessing, but can be measured objectively. For illustrative purposes, I created one example of each of the 5 categories or 4 categories of scoliosis relative to the normal spine. And here is the thoracic, scoliosis, lumbar scoliosis, thoracolumbar, as we discussed earlier. And here's a combined type and relative to normal. And when I apply the LCPC transform to these shapes, and I summed all the bins just as a quick index, you can see that the LCPC transform can quantify each of these types of categories distinctly. However, deep learning, without the LCPC transform, deep learning can quickly classify types of these 4 types of scoliosis, so there's no need for the LCPC transform for that. However, where the LCPC transform comes in very handy and can do things that deep learning can't, is in what I showed you earlier, that is precisely measuring these gradients, right, of improvement to track patient progress. Here in particular, I want to point out that if you compare the thoracic to the lumbar categories, right? They only differ in the position of this bump up here, right? And yet they can be measured very distinctly, right? And so in each of these cases, thoracic or lumbar, we can measure the gradient of, say, this bump moving progressively up, or this bump in the thoracic category moving progressively down. And in each case, we can measure that shape distinctly, that spine shape distinctly, even if the bump is the same, right? That we just shift gradually up or gradually down. And that's the power of the LCPC transform. It can quantify very precisely very subtle differences in shape. And these shapes, would not be detected robustly by measuring area or volume. So another test relevant to study of scoliosis is the bend over test, in which the physician then examines, right, the silhouette of the peak of the curvature in the patient. And here I just created a phantom series showing gradual improvement from 1 to 4. That is the bump on the right gradually leveling out. And here I applied the the parallel grid LCPC system to these shapes. And one index from these results that works well is dividing the value of bin 2 divided by over the value of bin 3. And that gives you a neat linear trend of decrease as the patient improves in response to treatment, which correlates nicely with the visual effect that we see in this phantom gradient. Now, alternative measures for the bend over test could be the curvature of the lumbar spine, right, when the patient is bent over. Here, this is a normal patient, and here is a patient with scoliosis. As you can see, there's a curvature here that can also be quantified, right? And these images can be taken from a smartphone, right, without the need for exposure to X-rays or CT scans. Another alternative measure of bend over test is just the shape of that affected side. That is here, the patient's right shoulder. You can measure just the bump. And here I've traced these by hand, which you can do in our software, or you can develop an automated pipeline that will automatically detect this shape in images in a way that's rapid and objective. Lastly, I want to point out the difference between deep learning and the LCPC transform, because this is a common question. Deep learning is great for rapid detection of images and shapes, and it requires the user to define ground truth, meaning if there are any subtypes that are outside of those defined categories, deep learning either won't see it or will ignore it. The LCPC transform, however, helps the user to define or discover new ground truth because it can measure, right, very subtle gradients that the eye has a hard time assessing. And the good news is that both deep learning and the LCPC transform can be combined for the best of both worlds, because once you've defined or discovered new ground truth using the LCPC transform, then you can teach deep learning how to find those new ground truths.